Mysore. For he has accepted our invitation to be a guest of honor, and he is one of our invited speakers. I ask our Professor Mahesh to introduce our guest of honor.
So, very good morning to you all. It gives me immense pleasure to introduce Dr. P. Sadashivegowda on this occasion. So, presently, sir is working as the principal of VVCE Mysore since from 2010. Dr. P. Sadashivegowda obtained his bachelor's degree in mechanical engineering with distinction in 1986 from University of Mysore. After that, he worked as faculty for about 3 years. In 1991, he earned his Master of Engineering in Refrigeration and Air Conditioning specialization from Coimbatore Institute of Technology, Coimbatore, through GATE. In 1997, he obtained his PhD in Mechanical Engineering from Indian Institute of Science, Bangalore. So, Dr. Sadashivegowda, he served at Renac India Limited as Product Development Manager for about 3 years, where he successfully designed and developed pre-coolers and liquid carbon dioxide coolers. In 1999, he moved to Kuala Lumpur, Malaysia, to serve as Faculty of Engineering in American degree program of Taylor's College, now Taylor's University. Later, he held the position of Head of the Engineering at the American degree program till 2007. He was given Excellence Award in 2004 by Taylor's College for his academic excellence. He joined Vidyavardhaka College of Engineering as a professor in mechanical engineering in 2007, and later he became head of the department of mechanical engineering. He was promoted to vice principal in 2008 and principal in 2010. He served as an academic senate member of PTU from 2013 to 2016. He is fellow of Institute of Engineers, executive member of ISHRE Mysore chapter, and life member of ISTA. His area of interest are refrigeration and air conditioning, CFD, and food preservation system. Now we are very curious to listen to his lecture on this occasion. So I welcome you, sir.
One second, sir. Sir, am I audible now?
Yes, sir.
Yes, sir.
Is my presentation visible?
Yes, sir.
Yes, sir.
Okay, thank you, sir. Firstly, I would like to thank SAPTHAGIRI College of Engineering for giving me this opportunity to talk on discretization. I would like to place on record my sincere appreciation and also thanks Dr. Ramkrishna, the principal of SAPTHAGIRI College of Engineering, and the HODs of Mathematics and Mechanical Engineering. I think we listened to a very wonderful talk by Professor Pradeep. It was very insightful and useful. And I'm talking about discretization, which is the basis of any computational, the computations. And this is my content introduction to CFD. I think most of you are familiar with the CFD, and I will quickly run through it. Then to understand the basics of discretization, and to understand the one-dimensional, two-dimensional, and three-dimensional discretization of heat conduction equations by control volume method. And normally it is done by finite difference. I will be using control volume method. And so then to understand the explicit Crank-Nicholson and implicit schemes. Now, what is CFD? I think Professor Pradeep G. Siddeshwar has demonstrated with a lot of examples, experimental values, and also theoretical values. Computational fluid dynamics provides a qualitative and quantitative prediction of fluid flow by means of mathematical modeling. Normally, we'll have partial differential equations. It could be the conduction equation, Navier-Stokes equations, all will be in the partial differential form. And numerical methods like discretization and solution techniques. This I'm going to talk about today. Then the software tools, there are many software tools that are used basically to solve these discretized equations. Sometimes we can develop our own software solution, but nowadays it will save a lot of time, particularly to solve CFD problems. CFD enables scientists and engineers to perform numerical experiments, basically simulation, in a virtual flow laboratory. And these are some of the applications. It is used widely in aerospace, automotive, biomedical, chemical, heating, ventilating and air conditioning, hydraulics, marine, oil and gas, power generation, sports. So I think there are many other applications where CFD is commonly used. Then if you look at the procedures that is adopted in the CFD, identification of right approximation, whether viscous, inviscid, laminar, turbulent flow, incompressible, compressible, whether it is single phase, multi-phase, this is one. Then the second is we are supposed to identify, the kind of fluid. The second one is identification of right solution method. It could be the finite element. It could be the difference, finite volume, structured, unstructured mesh, order of accuracy, depending on the problem and the accuracy required. Then we have the pre-processing. We need to generate the computational grid, assign boundary conditions, set initial conditions, compile code, and prepare input parameters. Then we have the solution. Basically, we run the code using some softwares, or we develop our own software. Then monitor the solution. And the post-processing, collect and organize data, analyze results. Basically, this is very important. Verification, this as engineers we need to do, that is, do the results make sense? Many times, sometimes, we get results that are nonsensical. So we need to analyze and assess whether the results make sense. Are the trends right? Does it agree with the previous calculations on similar configurations, maybe from the published data? Then the validation. Does the result agree with theory and the experiment? If you have a similar experimental setup, do they agree? Or whether we need to check whether the published data, whether the validation is an important step. Because something when we are trying to solve a very complex problem, it is important that validation play an important role. Then at every step, good understanding of theoretical fluid dynamics is essential. So then there are two types of prediction. One is experimental investigation. The other one is the theoretical calculation. And each has its own merits. The first one is, if you look at the experimental investigation, full-scale tests are useful, but they are very expensive and often impossible. And the alternative, perform tests on small-scale models, which can be extrapolated to full scale. Many a time we do, particularly in the aeroplanes, in aerodynamics. But important features may be lost during scaling. This is the disadvantage. Then the difficulty in the measurement. This is another difficulty we face with experimental investigation. Measuring instruments are not free from errors, and also the accuracy required may not be of required order. Coming to the theoretical investigation, it reports the consequence of mathematical model, not the actual physical model. So many a time the actual physical model is one, but the mathematical model will be totally different. In such cases, we are going to have a lot of problems. So mathematical model consists of a set of differential equations. Classical methods have limited scope for practical problems. So obviously we go for numerical methods. Variables are defined at discrete points. In case of numerical methods, it leads to a set of algebraic equations. This makes numerical method powerful and widely acceptable. So theoretical calculation gives implications of mathematical model and not the actual physical situation. This is very important. Many a time mathematical model is not, the governing equations are not written properly to the actual situation. The actual situation and the mathematical model may be totally different. They may not relate to one another. Results depends on the numerical procedure, what kind of procedure we are going to use, the accuracy of those procedures. Validation of mathematical model limits the usefulness of the computation. So of course we need to validate the mathematical model. And there are two types of problems. If you look at, one is classification. The group A, problem for which an adequate mathematical model is available, readily available or carried out. It can be carried out, for example, heat conduction problems, convection problems, simple turbulent boundary layer problems, where it is easy to write a mathematical model and also solve them. The other group is group B, where problem for which an adequate mathematical model is not worked out. So it means that it is very complex. Example, complex turbulent flows, non-Newtonian flows, and many other things that Professor Pradeep described. Then, and when you do research, these mathematical models, which are in the group B, transfer to group B. Because of research activity, the group B, some of the group B problems get transferred to the group B. So that is what, it's a continuous process. We propose a model, work out implications by computational analysis, compare with experimental data, verify, and thereby you transfer it to group B. Now coming to today's topic, that is discretization. Discretization of differential equations is called finite differences. If you discretize the partial differential equations, we call them finite differences. Discretization of integral form of equation is called finite volumes or control volumes. So I'm going to talk about this, how we can discretize the integral equations, and I'm not going to talk about how we can discretize the differential equations, because there you have forward difference, backward difference, center difference, and many difference we use in the discretization of partial differential equations. Now I'm going to talk about discretization of integral equations, call them finite volumes or control volumes. Now, how we do the formulation in the control? The first one is the computational domain is divided into a number of non-overlapping finite volumes, and we apply the conservation law each finite volume, which I will do for 1D, 2D, and 3D conduction equations. Then differential equations are integrated for each volume. So once we define the domain, then we write we consider grid points and then write the control volume, and we take the differential equation and then we perform integration. Then suitable profile expressing the variation of dependent variables are assumed. Okay, it could be a piecewise linearization or complete linear curve assumed suitably depending on the problem. Then resulting systemic equations are solved by some suitable methods. There are many methods that are available, like tridiagonal matrix algorithm. There are many algorithms that are available. Once we get the set of algebraic equations, we can use one or other method to solve them. Now, coming to the four basic rules in the control volume approach are: number one, before that, let me give the grid points. These are the grid points under the focus P. And we have another grid point to the west, that is W, capital W. And we have one more grid point to the right, that is E. So the west, east, and P at the center. And this small w is between P and W. It can be halfway through or it need not be equidistant. And small e is between E, capital P and capital E. And the distance, this is the control volume. That is small w to small e is the control volume in one dimension. And this is the distance at delta x. The distance, of the control volume in the x direction is delta x. And we have delta x w, that is from W to P. And then we have P to E, delta x E. So I think, if you remember W, that is west of P, and E to the east of P. And this is from small w to small e is the control volume. So that I'm going to talk about what are the four basic rules we need to follow in the discretization of the control by the control volume approach. And the first one is consistency at control volume. The control volume phases. It means what? If you take the control volume phase, this is the control volume phase. This one, that is small w, and the small is the control volume phase. So at this point, consistency need to be established. That is, the expression at the common phase of the two adjacent control volumes must be same. When the flux leaves the left control volume and the flux entering the right control volume must be same. So this consistency needs to be established. This is the rule number one, because when we write equations, sometimes, because of different slope, we may get different heat, you'll have one flux leaving, but when you take the calculation from the other end, it is different. So that should not happen. The second one is the positive coefficients. So what is positive coefficients? The increase in TE. If you look at T represents temperature at E must lead to increase in TP, because if you look at the grid, any increase in E must result in increase in P. Any increase in here must result in increasing at P also. Okay. And this is the second condition. And the third one is the negative slope linearization of source term. Invariably, we have source term where it could be internal acceleration or any other parameter that is contributing in the material. So we call it negative slope linearization. So that need to be, for example, I have written here, where S is the source term, consists of two components, SC plus SP TP. SP is a function of TP, where TP is, P represents the grid point, and SC is a constant. I have taken a linear equation. SC is constant. Okay, SP is a function of TP. So this term, SP, I think, it has to be negative. If it is not negative, what happens? If you look at, if the temperature, when you do the linearization, the temperature TP is increasing. But assume that this is also positive. Say you have a cooling system where you are cooling from higher temperature to lower temperature, and this need to be negative. If it is not negative, then divergence will happen in the solution.
And then a department level.
And the coefficient SP must always be less than or equal to 0. This is what I have mentioned. This SP has to be less than or equal to 0 for stability purpose. And the last one is sum of neighboring coefficients, which you will see when I write the equations. The T and T plus E, where C is a constant, must satisfy the differential equation and also the equations that have been discretized. So these are the four basic rules we follow in the control volume approach when you discretize the equations. Now, let me discretize the one-dimensional unsteady heat conduction equation with source term. Okay, this I have shown you already. I repeat, T is the grid point. This is the control volume from W to E. This is delta X W, and delta X E. And W, P, and T are the grid points. This is the differential equation. All of us are familiar with this. Rho C dt by dt equal to T K times dt by dx by dx plus S. S is the source term. Rho is the density. G is the capacity. And then this is the temperature. This is the temperature. Small t is the time. Okay. Let me discretize using control volume approach. If you do this, if I integrate equation 1, the equation is the one that I have shown you, for a control volume from W to T. So what I'm going to do, and also time interval from T to T plus delta T, I'm going to integrate this equation from W to E, okay, and also from T to T plus delta T. If I do that, I get this equation. And you also get on the right hand side W to E D dx dt and T to T plus delta T W to S dx dt. This is the source term. Okay, and this is the term. Basically, this term represents how we store the energy in the body. Okay, the rate of change of energy in the body. Now, if I perform the integration of this one, now let me show this one. This dt get cancelled. Then rho c assumed to be constant, and dt, the integration of dt will get t, and limits t to t plus delta t. And again, you get dx. I have retained as it. And if you look here, t plus delta t, then ke. Now I'm performing integration from W to E. Perform integration from W to E. If you go back and see, if you remember this one, dx get cancelled here. When you perform integration, d of this one, you will get k dt by dx. Apply limits, that is E. K dt by dx, you will get E minus k dt by dx W. You will get this one. So if I expand this one K, E, so because I'm applying at the control volume, if you look at this, I'll just show you the flow diagram. That is, I am applying here minus this point. This is the point, this is the control volume between P and D. This is the control, W is the control, the surface, you can call it, between the phase in one dimension between W and P. So you need to focus our attention from W to E. I am performing integration from W to E. I apply upper limit E and then lower limit W. And if I do it, what I get? KE, that is the upper limit, and then TE minus TP. Why do I get TE minus TP? Because TE is to the right side of the phase and the P is the left side, divided by the corresponding distance, delta XE. Similarly, I apply to the left side, that is small w. Then I get KW, TP minus TW by delta XW. And then what I do, I write dt as it is. Then you get here T to T plus delta T, SC. I have written this one, I have expanded. You will have a constant term and also the term associated with TP. And I am performing integration W to E, dx, you will get delta x, and dt as it is. And this is what? Okay, so I think easy to explain now. So this term I have taken for KE, TE, this is TE, minus TP. Divided delta XE, that is this distance. Similarly, for the lower limit, that is W, KW, okay, TP, minus TW divided by delta XW. That is this distance. So I think if you understand this, same thing applies for 2-dimensional and also 3-dimensional. Now let me proceed. And this is the W to E, rho C, T, the limit T to T plus delta T, I have applied, dx. This I have shown you already. And this is you get. Since here what I have written, T to T plus delta T, Tp dt, I have written Tp, it is a Tp dt. Then T plus delta T, I can take Tp prime or Tp. Sometimes we take at T, Tp0, at T plus delta T, Tp prime. So for example, like this also at T, Tp0 or T equal to T plus delta T, Tp prime also is considered. And this one, when I perform integration of this one, you will get dx, get delta x. And finally, I get Tp. It is, I am not, drop a Tp prime. Tp prime is the new time. This is the old time. So Tp minus Tp0, this at T, this is at T plus delta T times delta x. And you get this AE. I will explain what is AE. TE minus TP minus AW, TP minus TW times delta T. And I simplify this equation. And finally, what is AE? AE is nothing but KE by delta XE. If you go back, you will get this. AE is nothing but KE by delta XE. And AW is KW divided by delta XW. Then of course, DT, when you perform integration, DT will become delta T. Now you get this, after simplification, divide by delta T, you will get this equation, rho C, this one. And AP0, I will make another assumption, rho C delta X, because rho is a constant, C is constant, delta X is also can be made constant. Delta T, of course, you can make it a fixed value. Then you get this equation, AP0, TP minus TP0. There is no problem here. AP0 is nothing but this and AE. So you get a very simple algebraic equation. So finally, after simplification, on the left hand side, you will get AP0. AP0 is this, all the quantities. AE, that, KE by delta XE. AW, KW by delta XW minus SP delta X. And then on the right hand side, you get AE, TE. This is the new time. This is the old. So you will get this. And if you simplify, you will get AP. Yeah, I take like terms to one side, the terms that I need to determine, the terms that I know. If I segregate, I'll get a very simple equation. Okay, I will get this equation AP. So this entire thing will become AP. So AP TP. This is AP times TP equal to AE TE AW TW plus B. B is nothing but this entire thing is B. So you get a simple algebraic equation that can be solved by any one of the methods. So this is basically the discretization of one-dimensional heat conduction equation. I will extend this one to the two-dimensional. So how we do two-dimensional and also the three-dimensional. The control volume for the two-dimensional is this. This is W, capital W. This is one grid point. This is another grid point. We also have grid point here, and we have grid point here. And in the earlier one, we expressed the K, let's say KW, KE. Of course, they need to be expressed in terms of the grid points only, because you will not know the values at these points. That I will tell you later. Now, this is at north, south, west, east. And similarly, this is the control volume. This is the control volume. I have put small n, small s in the y direction. In the x direction, small w, small e. And I have also given this is delta x, and this distance, the control volume height is in the y direction is delta y, and delta xw, delta xe, which you are familiar. The other thing is delta ys to the south of w, to the north of w is delta yn. So how do we discretize this one? And let me write the heat conduction equation for this. This is rho c dou t by dou t and dou by dou x, k dou t by dou x, and then plus dou by dou y, k dou t by dou y plus s. This s is a source term. Now, in a similar way, what we are going to do, we are going to integrate this differential equation, partial differential equation over the control volume. Now, when we do the integration, this is the left-hand side. So we need to do t to t plus delta t, then south to north, okay, then west to east. In the same order, I have written these things. So you can, the innermost is dt. Next one is south to north, it is in the y direction. So I have written dy. And then x direction, that is west to east, dx. So it becomes easier when you perform calculations. Then similarly, this term, when I perform the integration of this one, w to e, I have written. Why I have written w to e? Because you have x here, k dou by dou x. So this x is normally x direction. That's the reason I have written first. And then north, dy, and finally t to t plus d, that is dt. Then this term, that is y. So here if you see, I have written first inside, the innermost integral is south to north. I have written y first for the simple reason that this differential equation, you need to differentiate with respect to y. Similarly, w to e, then I have written dx, and t to t plus delta dt. And finally, the last term, that is the source term. This you can write in any fashion, but we have written dx, then dy, then dt. Now, when you perform the integration, it is very, this dt get cancelled, and dt will become t. And south to north, this dy, when you perform, will get delta y after application of limits. W to e, this, you perform with dx, then this becomes delta x. Okay, this is, it will not be a problem. And similarly, when you perform integration here, this delta x get cancelled. Then w to e, this is d, this d of x is x. So basically you will get k dt by dx. K dt by dx you apply at limit e, and then w, and then south to north you perform with dy, you will get delta y, and then t to t plus delta you will get delta t. I'll show that one now. Okay. The left-hand side, you will get rho c, delta x, delta y, Tp minus Tp0. Why you get Tp minus Tp0? Basically, you apply the limits, t plus delta t to Tt. So t plus delta t is Tp, t is Tp0. Okay, so you get this equation. Then Ke, as I have mentioned, the way we did in the one-dimensional, Ke, that is in the x direction, Te minus Tp divided by delta Xe, then Kw, okay, Tp minus Tw, this also in the x direction, delta y, delta t, this is the first term. Let me, so that I can, okay, this is when I perform integration from this one, basically from P to E, so you'll get Te minus Tp, Te minus Tp divided by delta Xe. Kw, that is this. You get Tp minus Tw, Tp minus the upper limit minus lower limit, delta y, delta t. Then if you look here, the north one, when you perform, Tn minus Tp divided by delta y, that is this distance, delta yn, this is supposed to be small, into Kn. Kn is this, minus Ks, that is this, Tp is the upper limit minus lower limit Ts divided by delta y. And similarly, you perform integration with west to east, you'll get delta x and then delta t, and this is the source term. And you after simplification, you will get these terms, rho C and divide by delta T, you will get rho C delta X delta Y delta. You get these equations, which is self-explanatory, and S bar is this. And AP0, you combine the constants, and then AE, there earlier you got one dimension KE by delta XE. You have an additional term delta Y for AE, and similarly AW, you will also have another term. AN, if you will see, KN delta X delta YN, and AS also KS delta X. So this is an additional term compared to, of course, you did not have, for the one dimension, we had only this, but without delta Y. But in this, we have, because of it is two-dimensional. And finally, you will get, this equation, after replacing with constants. And after further simplification, we'll get a very simple equation given in 2D. So this is the one. After further simplification, you will get, this is a TP. So you will get this. AP is this much, B is this much. So AP TP equal to AET plus AWTW plus ANTN plus ASTS plus B is the constant. That is this. Now, I told you that, the positive, sum of the neighboring coefficients. If you see here, everywhere, AP, these are all the neighboring coefficients. It is sum of the neighboring coefficients. Similarly, if you see here, APTP is the, we are supposed to evaluate the temperature at the grid point P. AET is a neighboring grid point. This is also a neighboring grid point. Neighboring grid point to the right, neighboring grid point to the left, neighboring grid point to the north, neighboring grid point to the south. So it is sum of all these things. That is one of the 4 basic rules which I mentioned in the beginning. Now, let us move on. How we discretize? I think I have about another 7 minutes. Discretization of 3-dimensional heat conduction equation. How we do it in a similar fashion. This is the 3-dimensional heat conduction equation. Now you're all familiar with this. Rho C dou T by dou T. This is X direction, Y direction, and the Z direction. And this is the control volume. This I have shown in the 2D control. This is the 3D. And if you see here, this is the west, this is the east, north, south, we are familiar. Only thing is the 2 more, that is the Z direction, that is front, this is the back. So how do you write and how do we perform integrations of these equations? I'll explain in a while. Now, if you see, if I integrate that equation over the control volume in 3D, you get this. For example, you will get 4 integral signs. T to T plus delta T, dt, and W to E, dx, south to north, dy, and front to back to front. Why did I take front to back? I'll just show you. Yeah, back to front. Okay, the lower limit is back. Back to front, it is because the Z direction, if you see, it is in this direction. So I need to take in this direction only. That's why back to front, I need to perform integration. So if I do this, for all the terms, I get this equation. This is the left hand side term, and this is the first term. On the right hand side, second term, and the third term, and the last term, this is the source term. Then we need to perform integration of this. Very easy to perform because we know how we did in the 1-dimensional. I just repeat. One is I perform this dt cancel. You get dt t applied at t plus delta t applied at t applied t plus delta t. You will get tp t applied at t. You will get just tp0. And similarly, west to east, you get delta x. Then you will get delta y, and this one you will get delta z. So similarly, if you do here, this get cancelled, and then ke, okay, you are supposed to apply at the grid points, between the grid points or the control volume. So you get rho C is constant. As I told you in the beginning itself, we have made the assumption. In case you feel that they are not constant, so you have to express the way we are expressed thermal conductivity. Then it will become even more complex. So finally, you will get this the first term, Ke T minus Tp. This you are familiar. Delta Y, delta Z, delta T. Kn, Tn. This is the second term. This is you are familiar. This is the third term that we have taken. Kf, Tf minus Tp, delta Z in the Z direction. Kb, Tb minus Tb. This is the back front. Okay, so you get these terms and then the source term. So after applying, you get this. Then finally, if you divide the entire equation by delta T, you will get this rho C. This is by delta X, delta Y, delta T. There is a mistake here. So it is supposed to be delta T. Then you will get finally Ke. These are, if you see the one dimensional, you will get Ke by delta Xe. And then for the two dimensional, you will get Ke delta Xe into delta Y. And in the three dimensions, you get delta Z. So it is, all similar. We cannot go wrong in the derivation. And this is, these are all the constants, or I would say the coefficients. Okay, then, and these are all positive. If you see, all thermal conductivity cannot be negative. These distances cannot be negative. So all these coefficients are positive. AP0, this is also positive. And the B. And so you'll get, after simplification, you will get an equation like this: AP TP equal to AE TE, AW TW plus AN TN, ASTS, AFTF, ABTV plus B. And this is a very simple algebraic equation that can be solved by using any numerical method. I will spend just a few minutes, another 2-3 minutes on. We use, in order to solve these equations, algebraic equations, we may use explicit schemes. Okay, I will just take a one-dimensional unsteady heat conduction equation just to examine this. So you are familiar with this grid diagram, and this is the heat conduction equation without source term. And if you integrate this one the way we did in one dimension, no change, and you will get this equation. And finally, you will get a rho C, this equation. This is, of course, this is delta X, and T to T plus, you will get delta T. And now what we are doing here, when you perform TP dt, I am introducing weighting factor. The F is called the weighting factor. And this weighting factor can vary from 0 to 1. Okay, F equal to 0 means, what happens? This term will be 0. And this will be 0, and this 1 into TP0, get TP0. That is, when you perform integration T to T plus dt, TP dt, you will get TP0 delta T. Okay. So if F equal to 1, what happens? This term will be 0, this term will be 0, and this term is 1, TP prime. So TP prime delta T. See, when you perform integration, you will get TP prime. So if F equal to 1, it gives you the implicit scheme. If F equal to 0, it gives you the explicit scheme. If F equal to 0.5, then it is Crank-Nicholson scheme. So depending on the value of the weighting factor, you may get implicit scheme, explicit scheme, or the Crank-Nicholson scheme. So let me show you this with a diagram. Okay, so if you see, okay, this is the initial temperature of a body, and this is supposed to be after T plus delta T. Okay. TP prime. If you see TP prime, it is after T plus delta T. Initially, this is the temperature. And if you follow this line linearly, decreasing temperature, this is the Crank-Nicholson scheme. And this has a stability issue. So that's why, you have to be careful when you use Crank-Nicholson. And another one is, if you see here, TP is almost same. TP0 is equal to TP0 for the entire length of time, that is delta T. At the end, it drops to the new temperature, that is TP prime. And this is the explicit scheme. This, if you follow this, this is the explicit scheme. What is the implicit scheme? The TP0 at the beginning itself exponentially drops to TP prime. And then it will remain at that temperature the rest of delta T. Rest of delta means, this time maybe it may take a fraction of delta T. The remaining fraction, it will be at TP prime. This is the implicit scheme. And in fact, a fully implicit scheme is very stable. Explicit scheme is not stable. And the stability can also be checked based on the time factor, that is delta T. And if I continue the derivation of that, then what happens, if I divide again by delta T this equation, the one we did, I have just introduced the weighting factor and then perform that integration, and you will get this equation where AP0 equal to, okay, rho C delta X by T, AE equal to this. This, for one dimension, A is K by delta X, AW is this one. And you will get this equation. This is the equation you get with weighting factor. And if you substitute the weighting factor, let's say there are three cases: explicit scheme where weighting factor is 0. That means TP prime equal to TP0. Okay, so you will get, assume that I substitute all those things in that equation. You will get this, you will get, okay. You will get, if you please note here, AP0, you have a negative term here. So there is one stability criterion that need to be satisfied, that is AP0 has to be greater than AE plus A. See, B cannot be negative. B cannot be negative. Therefore, AP0 has to be greater than these two, the sum of these two. This is one important thing in the stability of explicit scheme. And what is AP0? AP0 is nothing but rho C delta X by delta T. And what is AE? KE. Assume that you substitute. Assume that KE equal to KW. The thermal conductivities are identical. And you get this equation. And if you simplify for delta T, you'll get this. So your delta T, that is the time factor, the increment in time, has to be less than this value. Delta X is very, very small. Multiplication of delta X times rho times C divided by 2K. This value has to be less than this, then the scheme is stable. Otherwise, explicit scheme will fail. It may, it will not be able to give the result. Now, the second one, the Crank-Nicholson, that is F equal to 0.5. Similarly, if you look at the stability criterion for this Crank-Nicholson, you will get, same thing. I have put 0.5 and then evaluated. Due to lack of time, I'm running through. And stability criterion for a Crank-Nicholson scheme is AP0. If you look here, you will get 0.5, 0.5. So AP0 has to be greater than this. This is the stability criterion. So if you have to determine that many a time Crank-Nicholson scheme results in oscillation. So that's why it is not recommended. But you have to ensure that AP0 is greater than these two values. That is AE plus AW divided by. And the third one, sorry, before that one, I'll just the Crank-Nicholson. Crank-Nicholson, this delta T has to be smaller than this value. Now, the third scheme is the implicit scheme. I said this is preferred because the stability wise is very good. And here F equal to 1. And if you solve this one, you get, if you look here, let me just AP, TP, and then B equal to this and AP equal to this. And then if you see, there are no negative sign here. There is no negative sign. AP equal to this. So all are positive. So therefore, fully implicit scheme is unconditionally stable. Whereas in other two cases, you had negative terms. With this one and this one had negative, but here it is not negative. So it is, even though you have a time delta T slightly big, still it doesn't diverge. So conclusion. So I have just briefly introduced the CFD, its applications and the formulation, and the basics of discretization. Even though it doesn't come under the ambit of recent advances in computational fluid dynamics, but this is very important to understand the advances in computational fluid dynamics. So this is basically the basics and how we use the control volume approach to discretize the heat conduction equations. So we have discussed one-dimensional, two-dimensional, and three-dimensional heat conduction equations. And also I have just quickly run through the explicit Crank-Nicholson and implicit schemes and the stability of those schemes in the current scenario. With this, I would like to thank. If there are any questions, I would be happy to.
Thank you, sir. That was an excellent session, sir. There is one question from Raghavendra Deshpande of SCE. The question is, how best discretization can be applied to irregular geometries and to satisfy conservation?
Sir, we can apply to the irregular geometry also. In fact, I have not discussed other, in fact, I prepared even for the radial and other things. It is applied, but as you know that if it is a regular geometry, it is very easy, but we can also use other methods to use, but control volume can be used for both regular and irregular geometries.
Thank you, sir. Thank you for your wonderful lecture. I am very much grateful to you as you have readily accepted our invitation to give the invited lecture. I hope we in future very soon, we want to hear you live, means on campus. So we want to invite you to the campus also to the fluid dynamics lecture session. We are planning for an international conference on fluid dynamics. So there we want you to be an invited speaker. Thank you, sir. Thank you.
Thank you so much, sir. Thank you so much for this opportunity.
Thank you, sir. I'll conclude, sir. For the participants, it is an off time for you now. Have a lunch. Join us at 3:30. Thank you. Thank you, one and all.